All right, and we are back, and we are with P, PD, PI, PID controller, and this is a PD controller. So we're working with no noise, no disturbance, plant function. Is the plant stable? And then we need to figure out what are, if not, the control parameters that will stabilize the system. So let's go ahead and let's define those parameters. So we've got, let's go ahead here, working from the last notebook. Whoops. So we're going to go, I'm going to say my CS is equal to KP, do a little KP, plus KD times S. I'm going to say PS is equal to S plus 4 divided by 10S squared minus 5S plus 2. So now, so it's asking us specifically if the plant is stable, and then the system. So let's go ahead. We're going to tackle a couple of these. So G of S is equal to CS times PS divided by 1 plus CS times PS. So let's tackle each of these at a time. Let's do full simplify. All right. So let's do our Ruth table. And actually, let's look at PS, even though we don't really even need to look at that. If we're doing the Ruth table for here, it's going to be 10 minus 5 and 2. So is this stable? Let's do table form. No. So this system is not stable, or the plant is not stable, excuse me. So if we want the system to be stable, we need to look at GS. So, and then I'm going to pull out the denominator here. We're just going to go full simplify. Even further, nope. But we can pull this out here below. And now we can do expand all. And now we can do our Ruth table. So our Ruth table here is going to be KD plus 10 plus KP plus 4 KD minus 5. Ooh, lots of S terms in there. Minus 5, and then it's going to be 4 KP plus 2. So only, yeah, this will be second order still. Excellent. So KD plus 10, KP plus 4 KD minus 5, and then 4 KP plus 2. Let's do table form. There we go. So now we have our expressions. So we can go ahead and say, all right, that we need, actually, there should be 3 values. Yeah, I think I made a mistake here. So 10 KD plus 10, comma, KP plus this. That looks better. All right. So we have several conditions. So let's go ahead and let's do reduce, and then we'll set up. So we need this to be positive. So we need this greater than 0. We need to be this greater than 0. And then finally, we need to have this greater than 0. Excellent. Squiggly. We need to have this greater than 0. Oops. No. That's not good. There we go. Thinking. All right. So, let's go ahead and look at some of these parameters. So, I like this one that's fairly simple. KD has to be greater than minus 10. KP has to be greater than 45. I'm pretty sure essentially that's an OR value here. So, we have some parameters. And actually, let's go ahead and let's try to visualize that. So I'm going to say my GS test is going to be equal to GS slash dot. I'm going to say KP goes to 60, and I'm going to say KD goes to, let's just put it 10. Let's also verify that that system is stable. So actually, we can do poll 0 plot simple. I can do my transfer function model GS test in terms of S. We can see if those poles are 0. We can also, and it looks like we are indeed good. So we have 2 zeros We have 2 poles. We're all on the left-hand plane. Let's just make sure, and we can do, I'm going to pull this Ruth table down here. It's always good to just double check. Let's do slash dot here, slash dot here. And there we go. So we are indeed stable. We verified that. And so now what we need to do is we need to plot some of these other values. So we're going to assume, and it should be stated in this problem, and it will be in your version that you see, RS is going to be equal to 1 over S. So that's R of S. Let's see. We're assuming no noise. And actually, we'll have to assume WS is equal to 1 over S as well for this problem. So let's go ahead. If there was noise here. So let's go ahead. Let's do the control effort. So my control effort here, we can remember that and hopefully have those plant functions not necessarily memorized, but we can use our table. So my control effort, C effort, will be equal to U over R. So that is going to be basically CS divided by 1 plus CS times PS. So that's my control effort. We need regulation. So regulation is going to be equal to, and then tracking error, E over W. So that's going to be minus PS divided by 1 plus CS times PS, or disturbance rejection. And then we can do tracking error, which is going to be error over R, which is going to be 1 divided by 1 plus CS times PS. Excellent. So we've got all those values. And actually, now we can plot all of them. Which of these values do we want to minimize, maximize? How do you achieve this? By modifying the controller. Illustrate with plots, with 2 plots for each. So let's go ahead. Let me make sure I need to change them. I'm going to change what that problem says. Illustrate with plots of each. So what we're going to do is we can say now, okay, my C effort, control effort, we want that to be not gigantic. And you can play around with that by changing essentially the magnitude of your K values. So my C effort is going to be equal to, or actually CT, let's call it CT, is equal to inverse Laplace transform of C effort times control effort is U over R, so it's going to be RS, S and T. So that'll be that plot. We'll also have art, we'll call it reg, or let's call it reg T. And that will be my regulation times my disturbance, which is WS. Why it keeps WS. And then finally, the tracking error. So just put that right here. My ET, error tracking, so we'll call it tracking error, track error, times my RS again. So we can plot all of those. So we can say plot, for example, CT from T goes from 0 to 10, and we'll do plot range all, at least for these values. Oops. So let's do CT. And I think we need, unfortunately, so we'll need to pick our values. Alternatively, you can actually just visualize and look at this, but let's look at it for the values that we picked and how we might change that. And actually, we can kind of do it a little bit, but still keep our system stable. And we can actually visualize this. So we don't need to see that anymore, but we need to see this. Excellent. So we can also do plot of here, CT, reg T, and then we can see our, what is it? What's our ET, air. So we can see here our air and our regulation are, we're actually really well, we're fighting against the disturbance quite well. Let's say if we increase those values. So let's say this was 100 and then this was 50. Let's see how these values change. So if we change this, then we can go back and see what like the minimum value is. So let's do 50, 50, 50. So if we run these again, we should expect, if I increase essentially the magnitude of my controller, right? You see my control effort increases. Now my error here is, or my regulation is improving, right? The values changed here. And so did this plot previously. So this matches our intuition. As we increase essentially the magnitude of that controller, it changes. What was our stability? I think we were like, let's say we put it like 51. And then let's put this at 1. So if we do this, we should see these values increase. Actually, excuse me. We should see when we do this here, we should see the controller effort decrease now. So we can see it's minus 30. Let's see that magnitude here. Actually, it's struggling a little bit, but then it kind of increases here. It's because we're right on the edge of stability. But you see here, we're worse on our regulation. We're worse on the air now as well. So actually, the initial effort of the controller actually increases here, surprisingly. But it's because we're right on that air value. So you can kind of see how effectively these values change. Excellent. So how do we tune this particular plant with a PID control for Nichols using Ziegler-Nichols method? So let's go ahead and do that. We're going to go ahead and put our system. So now we're going to call this is our PS2. PS2 is equal to 1 over s cubed plus 5s squared plus 10s plus 15. So when that happens, what do we get? So now we need to start to tune this particular plant. So when you're using Ziegler-Nichols method, remember that our first step in this process is we are going to give it a controller, and our controller is going to be our full PID controller. So CS2 is going to be equal to KP plus, let's just do KP plus KD times S plus KI divided by S. So our system, our G of S will still be, G of S is equal to CS2 times PS2 divided by 1 plus CS2 times PS2. Full simplify. So we got that GS. Should probably call it GS2. GS2 or RS, we're just going to keep it the same. And so now what we can do is we can say, okay, GS2 slash dot, and we're going to set KI to 0, and we're going to set KD to 0. And we're just going to tune the proportional controller first, or our gain. So we have our system here. Let's call it, I'm going to call it my new GS. So this is our new GS, and what we're now going to do is we're going to look at the time response. So I'm going to say my YT test is equal to inverse Laplace transform of new GS times RS, times RS, and then S domain, T domain, and we've got our value here. And that's going to be looking nice and not pretty, but it's okay. And what we're going to do is we're going to look at, and we're going to start to tune some of these values. So one of the first things that we can do is we can kind of see, we want to position the poles where we're almost, where we're marginally stable, where we just have the imaginary components here. So let's go ahead and let's expand this out. So let's expand all of this. So let's do our Routh table. And I have 1, 5, 10, and then 15 plus KP. So I want to put myself in the position where we're marginally stable. Let's do table form. So let's go ahead and let's solve that. So let's go ahead and reduce, and we're going to say I want this to be greater than 0. I want this 15 plus KP to also be greater than 0. So we need to be basically in between those values. So less than 35, or basically in between 35, greater than minus 15. So what happens if we're like at minus 14? So let's go ahead and look at, let's do pole simple plot, pole zero simple plot. Let's do transfer function model. And let's do our new GS slash dot KP goes to, let's go to like minus 14.9, because we would be greater than that here. And then we need to put it in terms of S. All right. So here we have that pole at 0, but we have these imaginary components too. It could be oscillatory, but I feel like it's decaying. What if we go to the opposite end? What if we do like 34.8? That's looking, maybe that's a little bit better. So let's go ahead and look at that system. So let's go ahead and see, let's kind of start to tune now the response. So I'm going to plot, what did I call it? Y test slash dot KP goes to, let's call it 34. And then let's plot from T goes from 0 to 10. Let's do comma plot range all. Let's see, what is our system? This is pretty good. So you see we're right at, we're trying to make these completely oscillatory. So 1.27, 1.2, like this is pretty good. If we go like 34.9, like I wonder if we put it right at 35, what's going to happen? And it's thinking, but this is already pretty good. But that's really good. I wonder what happens if we do 35. Put it perfectly right there. I think it'll start to increase. But we can also start to kind of pull out these functions to start to tune that response. So let's go ahead and tune the response. Let's go here. Now, even right at 35, we're looking pretty good here. So let's go ahead. I mean, let's just pick it. Let's go ahead. I'm going to get some coordinates. So I'm just going to try to pick here. I'm just going to get a rough estimate. I mean, this is a numerical approach anyways. And then I'm going to copy, get my coordinates. I'm going to copy here. So that's my period. So the period is that basically that KU value is just going to be what we set. So that was 35. And now we can essentially run the rest of these values here. So this will give me my Ziegler-Nichols KP will be whatever the KU is here. My Ziegler-Nichols KI will be equal to my KU and then the period. And then my Zn of KD will be equal to KU and the period. And then now we can plug that in and now look at how does the system look? How does the system respond? So let's go ahead and do that. So let's take our basically JS, or actually, excuse me. So let's go ahead. We had our GS, right? Or do we call it GS2? GS2. So GS2, so this is I'm going to call this my Zn GS, is going to be equal to this, slash dot, KP goes to this value here, KP goes here, KI goes here, and then this one goes here. KD goes here. So this is our new Ziegler-Nichols. We can go ahead and look and see pole, simple zero plot, transfer function model. We can visualize this ZNGS. That looks like a nice and stable function. Let's double check that our Zn yt is equal to inverse Laplace transform of Zn gs times rs st. We got that here, and let's plot Zn yt from t goes from 0 to 10, comma plot range all. Oof. We see it's a little bit of a funky response. We can see, are we really, is that we do have the oscillatory response. Ku would be the 192. And then we do have ZNGS. So we should be seeing that. Let's do I wonder if it would expand. Oh yeah, here we go. Looks a little bit better. There's a little jankiness at the beginning, but excellent. So we see essentially the response of that function, and we got it. Fantastic work. Finally, some conceptual questions. I want to improve the performance of my PID controller. I want to increase KD, decrease KI, and increase KP. This will result in a system with a decrease in rise time and settling time. So let's go ahead and let's think about this. So increasing KP, what will that do? So if I have KP and I increase, first of all, what is that going to do to the system? It's going to increase my natural frequency. So I'm going to increase essentially oscillations. My poles move further up the imaginary axis. So my omega n increases, my zeta damping ratio will decrease. So we're not changing the decay, and we should see an increase in essentially the control effort as well. So that's a really, really important component to the system. And remember, too, that we have essentially those expressions that we developed previously as well for our rise time and some of those parameters. And we can imagine essentially how those are going to change in relation to that omega n and some of those parameters. So let's go ahead and write those down. So my rise time, TR, is going to be equal to, we have that expression, 1.8 over omega n. So as I increase omega n, the rise time will decrease. So that is true. Decrease in rise time. My settling time, TS, is equal to 4.6 over sigma, and my sigma is equal to my damping ratio and omega n. So this value will basically be constant. So if I increase KP, I'm not necessarily shifting this at all. Actually, it's not going to change at all. So maybe that's not true based solely on KP. Now, what happens if I increase KD? Well, we know that KD is effectively going to shift. It will shift essentially those poles. So KD effectively increases my dampening, right? So my eta increases, right? I have more damping, and I get a shift. So my damping ratio of KD will increase, and I get my omega n is unchanged, and my poles sigma will move to the left, or they get smaller. So if I increase KD, I am going to get more damping. The poles move leftward. I have more stiffness. Excuse me, not more stiffness. I have more damping. So those will move to the left. And so if this gets larger in magnitude as I increase KD, then that's true. So I will actually also get an improvement in settling time. However, oscillations of the system response increases. Yes, that's true if I increase KP. And the effective dampening increases. That is true because I'm getting, that's from KD. So KP increases the oscillations, KD increases dampening. That is also true. The system will improve the steady state air, but has a tendency to overshoot. Is that true? So what is KI doing? KI, as we increase, it will improve steady state air, but it is also true that we can have we have basically this pole at the zero, we have a third order system, and it can overshoot and maybe perhaps basically create an instability and become unstable if we exceed a critical value. So overall, I think this statement is true, but we want to break those down. So look forward to that one on the exam. And that's it. I'll see you next time. Thanks. Bye.